This video is going to pretty much go over this entire equation, except I'm going to show you specifically how you're going to be able to solve for every single variable within this equation, and then probably take it a little bit further when we actually do the solving for temperature, should you want to do that. My advice would be that when I put the timestamps on this video, if you're looking for one in particular, so like let's say you're trying to solve for mass because that's the one variable that you know you're trying to find, but you're not exactly sure how to go about it, follow the timestamps, and each individual section of this video is going to be dedicated towards solving each of the variables. Now, to provide this video with the intro, first of all, I'm going to tell you what every single variable in this equation actually means, if you don't know. And it's a good thing to have a reminder, that way, should you actually decide what you need to find, you can go ahead and just skip ahead. First of all, Q. Q means heat. And in particular, in the context of the equations that you guys are going to be doing, heat is going to be measured in joules. So anytime you ever see anything referred to energy or joules or kilojoules or even calories, technically, you're definitely talking about heat, at which point you know that any number that means that is going to go into the heat placeholder variable, whatever you want to call it. Alright, M. Well, M is pretty straightforward. M is essentially mass. Now, the importance about this one is that your specific heat will actually dictate what mass you're going to be using. In this case, though, you're probably going to want to go with grams. And so what that means then is, if you end up having kilograms, or if you have ounces or pounds or whatever, it doesn't matter. However you're measuring weight, you're going to want to convert to mass. Now, C. C is the one that ends up being a little bit more difficult to understand, because C is the specific heat capacity. And the specific heat capacity is essentially related to how well a material is able to heat up and resist changes in temperature depending on how much energy it's actually taken in. In this case, specific heat capacity is more than likely going to have the units of joules per gram degrees Celsius. And for that one, you're honestly just going to have to select it depending on whatever material you're heating up or the problem is talking about. Water, copper, wood, it doesn't matter. Just focus on the material. All right, now the last one. This is change in temperature. So delta means change in, and by delta I mean I'm referring to this triangle thing. That's the delta. Okay, so delta T refers to change in temperature, which means you're probably going to want to know either the starting point of your temperature and the final point, or maybe you'll get lucky and they'll straight up just give you whatever the change in temperature is. It just really depends. But regardless, if you have to calculate the delta T on your own, this is how you do it. Delta T is equal to the final temperature minus the initial temperature, so whatever temperature you started with. And then once you have that, you're pretty much good to plug in. These are the basics of the calorimetry equation. But if you're trying to solve for each individual variable, I would recommend that you go ahead and just follow the timestamps for the one that you need from here on out. Case 1 problems are honestly probably the easiest, because you're essentially going to be using that equation that we had literally just to find the energy, which is the whole point of why you even have that equation to begin with. So in case 1, normally what will happen is that they'll give you every single variable except for energy, which means that you're going to need to actually go by and find mass, specific heat, and change in temperature. Now, when you're doing these problems, one of the best things you can do is have the equation written out. So Q is equal to MC delta T. And then have a tally, or have like a running mark of what it is that you're going to be looking for. Now, you don't necessarily have to do this if you really understand what you're doing, but this is a good way just to keep track of everything that you're trying to find in terms of information, what's useful to you. And honestly, it just helps you stay organized, so that when you decide to plug in stuff into the variables, you're pretty much set to go. So we need to find heat, we want to find mass, we want to find specific heat, and then we want to find change in temperature if necessary. So let's just read through the problem and see what we have. Okay, so at the top it says how many joules of heat are required to raise the temperature of 550 grams of water from 12 degrees Celsius to 18 degrees Celsius. Okay, so right off the bat, the how many part, so how many what, how many joules. Okay, well that just straight up already tells me that I have no clue what my heat is going to be, which means I'm probably going to need to find it. And then it says, okay, well, they're required to raise the temperature So raising the temperature means that you should expect a positive heat, because you're going to be going from a lower temperature to a higher temperature. Now, how much in particular? Well, it says 50 grams of water, so we now found the mass, so we know it's going to be 550 grams of water. And then the other thing that it finally says is, well, you're going from 12 degrees Celsius to 18 degrees Celsius, which means in order for us to find our delta T, we're going to need to actually calculate it out. So we're going to have to go T final minus T initial, which in this case, if we went from 12, that's our starting point. So 12 is going to be over here. And then we eventually went from 12, and then we rose the temperature. We went all the way up to 18, which means 18 is going to be our initial. I'll try to draw that a little bit neater, but it doesn't really matter. At the end of the day, what you end up getting is that your change in temperature is going to be 6 degrees Celsius. And then finally, well, specific heat. Okay, now here's the clue. When you're doing specific heats are entirely dependent on the material. And here you have an entire table of specific heats. In this case, what you want to do is, when you're going to be looking through a problem, you want to highlight what it is that we're heating up. In this case, it's water. We want water, which means when we're trying to find our C, we're going to have to come up here to the table. We find water. We see that water is 4.184 joules per gram degree Celsius, so 4.184 joules per gram degree Celsius, and then we finally now have every single variable except for the one that we're trying to find. Now we're good to plug in. So we don't really know what Q is, so that's what we're trying to find. Now we know the mass. The mass is 550 grams. We also know the specific heat of water, which is 4.184 joules per gram degree Celsius. And then finally, we know the change in temperature, the delta T, which is 6 degrees Celsius. And then honestly, from here, it's just pretty straightforward. What you're going to notice is that your grams are going to cancel out. Your degrees Celsius are going to cancel out. You're going to be left with joules. And then all you really have to do is just multiply straight across. And that will essentially give you your heat, whatever it actually is. And what you'll find is that your heat is 13,807.2 joules. So to contextualize this, because you always kind of want to do this whenever you make a problem, what this means then is that you're going to need 13,807.2 joules to put into water, into specifically 550 grams of water, to get it up from 12 degrees Celsius to 18 degrees Celsius, or really just to make it increase 6 degrees. And so that is how you do a straightforward, problem where you find the energy. In this scenario, which I'm going to call case 2, you're trying to find the mass this time. And this is going to be slightly more complicated because it's not going to be as simple in case 1 where you can just go ahead and multiply everything through. You're going to need to actually consider dividing. So in here, again, for every single one of these problems, it's always going to be the same idea. You list out whatever variables you know, you identify the one that you don't know, and then you just pretty much plug stuff in, let the math take you wherever it needs to take you, and then you should be able to get your answer. So to read the problem and annotate it, all right, well, first of all, we have 8,750 joules of heat. So right off the bat, we know the heat. We know that we have 8,750 joules. Cool. Then it says what? Okay, well, it's applied to a piece of aluminum. Okay, we know it's aluminum, which means the second we figure out what material, we can totally find out whatever C is. All we have to do is look up at the table. In this case, we see that aluminum is right here. Aluminum has a specific heat of 0.89 joules per gram degree Celsius, so that's what we're going to use. We have 0.89 joules per gram degree Celsius for our specific heat. And then the next thing that it says is, when you apply that heat, you're going to cause a 56 degree increase in the temperature. Okay, we're not talking from one temperature to another. This problem is actually doing us a bit of a favor and is telling us directly that we already know what the increase looks like, which means if we know the increase, we know the change in temperature. The change in temperature is just 56 degrees Celsius. So we don't actually have to do the whole T final minus T initial thing here. It's just a matter of going 56 degrees Celsius, and then we know the change in temperature. So at the end of it all, well, what is it asking us to do? Well, it says, what is the mass of the piece of aluminum? So the one we're trying to solve for ultimately is mass. Okay, so now that we have all the variables laid out, all we really have to do is just plug them into the equation and set everything up the way it's supposed to be. Okay, well, we have 8,750 joules is equal to, well, we don't know the mass, so I'm going to go ahead and just write M to represent mass. We know specific heat is 0.89 joules per gram degrees Celsius, and then we also know that the change in temperature caused by that energy is 56 degrees Celsius. So from here, all you really have to do is do the math. Now, there's multiple ways to do this. The way that I like to do it is that I know that the variable that I want is right here. So according to algebra, normally whenever you want to try to solve for the variable that you want to get rid of everything around it. So in this case, we know that this M is going to be multiplied by the 0.89 joules per gram degrees Celsius. And then we also know that it's being multiplied by the 56.0 degrees Celsius. So one very fast way to do this would be very simple to do this. You just divide both sides by 0.89 joules per gram degrees Celsius, so by the specific heat. So what I do to one side, I do to the other. So over here, I'm going to do the same division. And what that's going to do really is that this now is going to be able to get crossed out. So we moved it over to the other side. And then right here, I'm going to divide this 56 degrees Celsius out, put it on the other side. And what you'll notice is that this is going to cross out too, which means all you're really going to be left with once you do this math is essentially just going to be M, which is exactly what you want. You want to find the mass. So your mass is going to be equal to this math equation right here, pretty much. So it would be 8,750 divided by, and then what you're going to want to do is you're going to want to do this thing on its own. That way you follow through. And what you'll notice too is that your degrees Celsius are going to cancel out. And then pretty much everything is going to set up and cancel out, and your answer is going to be finally in grams. So assuming that you take this whole thing right here and you plug it into a calculator, you will eventually get your answer, which is going to be approximately 175.56 grams. So this is the mass of the piece of aluminum. Now again, this is assuming that you pretty much set everything up and do the algebra in such a way that you can go ahead and just plug stuff into your calculator and then let your calculator do all the work for you. So we now know that in this case, for this problem, what it was asking us is, well, the mass of the piece of the aluminum, it's 175.56 grams. Here we have case 3, which is specifically problems that are asking you to find specific heat. Now, obviously, we are already ahead of time knowing that we're probably going to be trying to find the specific heat, but I do still want to approach this problem as if we didn't know, which means I'm going to go through the word problem, I'm going to annotate it, and then we're just going to see what we have and then see how we can plug them into the equation to find what it is that we don't actually know. So, reading through the problem, we see that if we have 4,786 joules of heat, okay, so right off the bat, we already know the heat, we know Q. The Q is going to be 4,786 joules. Okay, well, let's continue reading. So 4,786 joules of heat are going to be transferred to an 89 gram sample. Okay, so now we know the mass because we see grams. So 89.0 grams sample of an unknown material. Okay, so the sheer fact that it tells me unknown material means that I'm not going to be able to go find the specific heat. So that's already telling me pretty straight up that I really don't know what my specific heat is going to be. Now, we're going to need to confirm that later on to the problem, but let's keep going to see what else we see. Okay, so sample of an unknown material with an initial temperature. Okay, so an initial temperature of 23.0 degrees Celsius. So right off the bat, when I see the word initial, I'm probably going to have to consider that I might have to calculate the change in temperature on my own. So let's keep reading then, just to keep that into the back pocket. Okay, what is the specific heat of the material? So now we definitely know we're trying to find the specific heat. And then it says if the final temperature is 89.5 degrees Celsius. So we know that we have the initial temperature and we know that we have the final temperature, which means unfortunately we're going to need to calculate our change in temperature in this case. And now remember, Change in temperature is final temperature minus the initial temperature. So in this case, our final temperature is right here. Final temperature is 89.5 degrees Celsius. So 89.5 degrees Celsius. Our initial temperature, again, was right here. So it's going to be minus 23.0 degrees Celsius. And when you do the math, you're going to find out that this material, whatever it is, experienced a temperature change of about, let me see if I can do this in my head, 66.5 degrees Celsius. Okay, so we now have every single thing that we need. All we got to do now really is just plug stuff into the equation and then continue from there. So to remake the equation given the numbers that we have, well, we know Q is 4,786 joules, and Q is always equal to mass times specific heat times change in temperature. So we know the mass. The mass is 89.0 grams. We do not know the specific heat, so I'm going to write that as C. And then finally, we definitely know the change in temperature. The change in temperature is just 66.5 degrees Celsius. So like in case 2, or like when you're trying to find mass, in this case we're not going to be able to multiply perfectly straight across. We are going to have to divide. The whole goal of what we want to do here is that we want to get this C on its own. And right now this C is being multiplied by the 89.0 grams and by the 66.5 degrees Celsius, which means in order for us to get the C on its own, we're going to need to divide, well, first of all, by 89.0 grams so that we can go ahead and get rid of it here. That means what we do to one side, we have to do to the other, so we're going to have to divide by 89.0 grams. And then we're also going to need to divide by the 66.5 degrees Celsius so that we can get rid of it on this side, right? So because these will cancel out, these will cancel out. And then on the bottom we get 66.5 degrees Celsius. And what you're going to find out really is that once you do this, this is the math that you're going to need to do to find the specific heat of what it is that you want. So let me rewrite this just to make it a little bit cleaner. So C is going to be equal to 4,786 joules divided by 89.0 grams times 66.5. So this obviously again has to be done together in your calculator. And then you're going to find out that your specific heat for this material is going to be equal to 0.8087 joules per gram degrees Celsius, because again those are the units of specific heat. So here you have your final answer if you're trying to find specific heat. Here we have the final case, which is when you get a problem that requires you to solve something regarding temperature. Now, these problems are a little bit more difficult in the sense that they might just require you to solve for the change in temperature, but sometimes they might have you take it an extra step and they might have you use that change in temperature to find out like an initial temperature or a final temperature. It just depends. So, same process. We want to start out by taking all of the variables that we have and then seeing what we know about all of these. And obviously that's going to require us to read through the problem, so I'll read through it now. So we have a 250 gram sample of water. Okay, so 250 gram sample of water, probably going to be the thing that's going to heat up. This is going to do us a huge favor because the 250 grams is the mass, and then right off the bat, because we know it's water, we should be able to find the specific heat if we need to. So water, right there, 4.184 joules. So specific heat of water is 4.184 joules per gram degrees Celsius. Cool. So right off the bat, within the first 5 words, we have 2 things. So we'll keep going. Okay, so a 250 gram sample of water with an initial temperature of 98.8 degrees Celsius. Okay, so we have an initial temperature. That is something to keep an eye on. Now, what about that initial temperature? Well, this sample of water loses 7,500 joules of heat. So we now know our Q, 7,500 joules of heat. And then it says, what is the final temperature of the water? Okay, as you can see down here below, we know heat. Actually, let me do this with a different color. We know heat, we know mass, and we know specific heat. But we do not know change in temperature, which means that is the guy that we're going to shoot for. Okay, so then let's contextualize that. We'll put a question mark right here, and then we'll just try to solve for it. So our heat, we said, was 7,500 joules, and that's going to be equal to the mass of the water times the specific heat of the water. And then finally, we're trying to probably find the change in temperature. Like in case 2 and like in case 3, we're not really going to be able to just multiply straight across like you normally can when you're finding heat. We're actually going to need to try to find delta T on its own, which means right now while we're looking at delta T, it's being multiplied by the 250 and also by the 4.184 specific heat of the water, which means if we want to undo all of that and we want to get delta T on its own, we're going to need to divide by 250 grams on both sides, sorry. So 250 grams on both sides. This is going to be canceled out. And then we also need to divide by 4.184 joules per gram degrees Celsius on both sides as well, so that we can finally get our delta T on its own. Now in doing so, again, everything else except for the delta T is going to cancel out. And here I'm going to show that. But what I'm going to do to mop this up a little bit is I'm going to take the delta T and I'm going to write it over here on the equal sign. So delta T is equal to pretty much whatever this is going to equal in your calculator. Now again, I'm going to assume that you know how to plug this into your calculator. And this is going to be 7,500 divided by whatever 250 times 4.184 is equal to. And you're going to find that your delta T is going to be equal to about 7.2 degrees Celsius. Now the thing is, if the problem was asking us for change in temperature, you would actually be done here. If you know the problem is straight up just asking you for change in temperature, you would go ahead and just say 7.2 degrees Celsius and you'd be finished. But this problem is not asking for that. It's asking for the final temperature of the water. That means we need to take our delta T and really think about it. So delta T is equal to the final temperature minus the initial temperature. Now we know the initial temperature, so we know this guy, and we also know the delta T. So all we really have to do is plug in and solve for T final because that's what we know. Okay, so change in temperature was 7.2 degrees Celsius, and that's going to be equal to whatever the final temperature is minus, well, our initial temperature was up here. It was initial temperature is 98.8 degrees Celsius, so 98.8 degrees Celsius. And from here, it's just honestly going to be simple addition. You add the 98.8 degrees Celsius to both sides. It's going to cross out here. You add it over here, and you get 98.8 degrees Celsius. And what you're going to get is that your T final is equal to about, well, what would that be? Well, the 0.2 will give you a flat number, so that'll go 99 plus 7. So it's going to be about 106 degrees Celsius. Regardless, again, the main idea with these problems is you're going to want to try to solve for delta T. Treat delta T as a variable and then just do everything you've normally done in algebra to try to solve for the variable once you know what it is.